Hi everyone, today I'll be doing the second part of the improper integration. Okay, so last lesson we have done this, so we already done this part, so I will box it up. So this part we have already done. Okay, so this part we already done for infinite interval. So for today's lesson we'll be doing fx is unbounded. Okay, so we'll go through again on the meaning. So there exists at least, so there's at least or a vertical asymptote at x equals to a or x equals to b, or there's one more possibility, x equals to c. So where is c? Where c is in between a and b, whereas a is less than c and c is less than b. So that means c is somewhere between the interval of integration. Okay, so another thing I need to highlight is, so fx is discontinuous, so this is not very precise. We cannot just say is discontinuous. Okay, we must mention about it is infinite discontinuous, infinity discontinuous. So fx is infinity discontinuous. So discontinuous at where? At the x value where they give where the graph have the vertical asymptote. Okay. So and also another thing I want to highlight is VA. So the word VA, vertical asymptote. Okay. As we go along, I will use VA. VA is your vertical asymptote. Okay. Instead of spelling out the whole word vertical asymptote, I'll use VA. Okay. So we can begin now. So first, I will say that the VA is at x equals to a. So first consideration. Okay, let's say the graph or fx have a vertical asymptote at x equals to a. So how does the graph looks like? So just a guide. So the graph may looks like that. So x equals to a. So it could be like that, right? So this is your b. Okay. So other information is we have to know this value. So before a, your x value can reach this part. So this part is not a, but is a plus, because slightly more than a, right? The x value here is slightly more than a, so you put at a plus. So by using the notation a plus, and we know that x equals to a is an asymptote, so we have to use a limit to express our improper integration. So you write integrate a to b fx dx. So I zoom in, then we say equals to limit, so we put limit. Now we use another alphabet, c approaches to a plus. Okay, a plus, because the a plus is a value that is slightly more than a, which is in this scenario. So this is your a plus. Okay, so as x approaches to that, we have the integration c to b, right? Fx. Fx dx. So with this in mind, we can, so again we go through, we know that integrate fx. So integrate fx is capital Fx, right? This is your indefinite integral, so you just put in your fx, so limit c approaches to a plus, so square bracket fx b c, right? Now then we use our integration, c approaches to a plus, capital fb. Now fb will not involve c, so will not involve a, so we just write capital fb minus limit ca plus fc. Okay, so that's how we find the improper integral for this discontinuity, infinity discontinuity at x equals to a. So same thing, I will encourage you to write on your cheat sheet for this situation where fx is having a infinity discontinue at x equals to a, so it's equals to this. Okay, next we will consider your vertical asymptote at x equals to b, right? Which is the endpoint, one of the endpoint in your interval. So we draw the graph. So x equals to b maybe is here. So we could be like that. So your a is here, right? So again, you observe that this point, this value is b minus, right? B minus. So you define a c that approaches to this value. Okay, you define a c value in your improper integration that approaches to this value. Okay. So how do we write? So we write integration a b fx dx. So it's equals to limit c approaches to b minus. So your b here will be replaced by c, right? Because of the approaches to b minus. So integrate a c fx dx. Okay. So next you bring your fx, capital Fx, after your, which is the result after your indefinite integration. So capital Fx. So you write ca. So you can simplify. So limit c approaches to b minus square bracket fc minus fa. Okay. So similarly, I will encourage you to write this in your cheat sheet. So this is your formula. Of course, you must recognize that b is your asymptote, which give us the infinity discontinuity. Okay, so the last infinity discontinuity will be when the VA vertical asymptote at x equals to c, where c, a is less than c and c is less than b. Okay, so your asymptote is in between your intervals of integration. So this is your asymptote. So let's say you have this graph, and then something like that. So this is your c. So this is your a, and of course this is your b. So you're talking about here to here, right? So then again in order to use the limits, we have to identify this value here, slightly less than c, so c minus, right? So you use a notation, another alphabet. Let's say we use d, approaches to c minus, and here c plus, so we use c plus here. Then we can say e approaches to c plus. So now, how do we represent the improper integration? We say integrate ab fx dx. So we broke into two parts, from a to c and then from c to b. So we say it's equals to a to c, and then from c to b. Okay, so I'll concentrate on this. So you see this will be equals to, so you bring your limit d approaches to c minus integrate ac fx dx plus limit e approaches to c plus integrate e to b fx dx. Okay, some minor correction. This is not c. Okay, so this is not c, this should be d. So please, in case you forget, so it has to be replaced. So already replaced with the limit. So now you use your capital F. So your capital Fx square bracket d to a plus limit fx b to e. So now you bring in your limits. So the first one is limit d approaches to c minus fd, right? Minus fa plus fb minus limit e approaches to c plus capital fe. Okay, so we have to evaluate this limit. So similarly, I will advise you to memorize or to put this into a cheat sheet. This, and this is the result. Or you can start from the, or you can use the whole working, or you can show the whole working in your presentation. Okay, so a few things I need to mention is the limits. So all these limits, this and all these limits, and this, so all these limits may require to use L'Hopital rule to calculate. So we need to use L'Hopital's rule. Okay, so there's one thing I want to say. So we need to use L'Hopital's rule. So another thing is, similarly, we have to investigate for each limit. If the limit exists, then the improper integration will give a value. Now if the limit does not exist, then we say the improper integration is divergent. Okay, so similarly, words of caution, you must know, if the limits means all the value you calculate for limit, if the limit exists, so the improper integration will give a value, right? Improper integration will evaluate, okay, to a value, that means there are maybe 1, maybe 2, or maybe 3. Okay, now second point, if the limit does not exist, any of the limit in any situation does not exist could mean infinity, or the value of the limit changes, alternating or changing as your x value become larger or very small. So if the limit does not exist, we say the improper integration is divergent. So let me expand this. Improper integration is divergent. Okay, very similar to your previous lesson, okay, which have this concept of divergent and convergent, or exist or not exist. So same, limit exists, then improper integration evaluate to a value. Limit does not exist, improper integration is divergent. Okay, so these are the things that you have to look out, have to be mindful, or have to be aware of. Okay, so the next thing I want to do is to show you how to apply this way of doing in your example. Okay, this is your first example in your slide. So now the first step is to identify vertical asymptote, the VA, okay, for our integrand. Integrand means the function that you are going to integrate. So usually we call it the fx, right? So integrand is your fx. So first let's say fx equals to 1 over square root 4 minus x. Now to find vertical asymptote, you will solve. So vertical asymptote occurs when the denominator is 0, right? So we have to, so you say 4 minus square root 4 minus x equals 0. So as you solve, x must be 4, right? So say therefore fx has an infinite discontinuity. At x equals to 4, right? So that's the first thing. And coincidentally, our upper limit for the integration interval has 4. So this satisfied the improper integration of infinite discontinuity. So second step will be, so you integrate 1/4, or you can find the integration of 1 over square root 4 minus x first. So no matter how, you still have to find this integration. So you integrate as per normal. So we have integrate 4 minus x to the power of minus half, and then it will become 4 minus x minus half plus 1. So minus 1 bracket minus half plus 1. Of course must plus c, right? But during our improper integration, we don't need to include the plus c. So you get minus bracket 4 minus x to the power of half plus c. So then we say therefore integrate 2 4 1 over square root 4 minus x dx must be limit. Now you are going from the less than 4, right? So you say b go to 4 minus, right? Integrate 2 4 1 over square root 4 minus x dx. So first you write down the improper integration using limit. Now second step, you can bring in your capital F, right? So you can write limit b 4 minus, so you get minus bracket 4 minus x half. Sorry, this is no more 4. I have to change, change to b. So this must be 4b. So there's a b here. So you change to b. So this is b and then 2. Now because of the negative sign, okay, you can swap the limit if you want. So you get limit b 4 minus square bracket 4 minus x half. So swap the limit, the 2 go up, the b come down. So once the negative sign is removed, you can remove it by swapping the limits. So now you use the 4 minus 2 half minus limit b approaches to 4 minus bracket 4 minus b half. So of course this is square root 2. Now this one will become 0, right? Because 4 minus 4 is 0. So the answer is square root 2. Okay. Now the second part of the question, interpret your result geometrically. Okay. Now how to interpret? So geometrically, so means is to use a graph. So roughly you have to be able to sketch the graph of 1 over square root 4 minus x. So let's try. So fx, so let's try to draw the graph. From 2 less than x less than 4. So this is your domain. So okay, so when x equals to 4, there's an asymptote. So draw a vertical asymptote 4, right? Now from 0, so 0 you put inside, you get square root half. So you get half. Square root 4, you get half. So half is here. So as the x value increase, okay, so when you include 1 over square root 3, so 1 over square root 3 is still greater than half, right? So let's try. 1 divided by square root 3. Yeah. So as you estimate the graph, okay, as you estimate the graph, you see that the graph is going upwards. Okay. So when we do integrate, so that means integrate 2 is here, right? So when you put 2, you get 1 over square root 2. So 1 over, sorry, 2 is not there, 2 is halfway. So you can, this is your 1 over square root 2, right? So when you integrate 2 to 4, actually you are finding the area, right? So this area, so we say area, so geometrically, so we answer so geometrically integrate 2 to 4, 1 over square root 4 minus x dx represent the area of the graph, area under the graph, or area bounded, area of the graph of y equals to 1 over square root 4 minus x from x equals to 2 to x equals to 4. So there is a geometrical interpretation. Okay, now we can go to the next example, which is the last example for this section. So this is our last example, example 9. So in order to do the integration, you may need to find the infinite discontinuity of ln x. Now reflect the graph of ln x, so we can reflect on the graph of ln x, which is like that. This is 0, this is y equals to ln x, and this is 1. So 0 to 1 means from here to here, 0 to 1, right? 0 to 1 will be here to here. So which means there's a infinite discontinuity at x equals 0. Okay, so we already found it. So this part will be infinite discontinuity. So no matter how, we still have to integrate it normally. So first, to integration without limits, that means you have to do this, you have to use the by parts, right? So integrate 1, you get ln x, minus integrate x times differentiate ln x. So we get x ln x minus integrate 1 dx. So we get x ln x minus x plus c. So actually the c, you don't have to worry. Okay. So next, now we put in our integration with limits. So it come out to be an improper integration because of the infinite discontinuity. So we say limit. Now we say a approaches to 0 plus, right? Because here is more than 0. Okay. Integrate a 1 ln x dx. So you bring in our integration result for our indefinite integral. So bracket x ln x minus x. So no need to put in the c. So from here, we know there is 1 ln 1 minus 1 bracket minus limit a to a approaches to 0 plus a ln a minus a. So ln 1 is 0. So eventually this one become minus 1 minus. Now that means you must limit the whole one at a time. A approaches to 0 plus a ln a plus limit a approaches to 0 plus a. Okay, obviously this one will become 0, right? so there's no worry. Now this one will be a bit tricky because this is 0 times ln 0. Now ln 0 is negative infinity, remember? So this one have to solve by L'Hopital rule. So we have to transform into fx over gx, the ratio. We'll bring down the a. So it become ln a over 1 over a. Right? So with this we have a fraction. So in this way we can use the L'Hopital rule. So equal. So we have to differentiate, right? So we just put a prime here first. Okay. So it become minus 1 minus limit a approaches 0 plus. Differentiate ln a is 1 over a. Differentiate 1 over a is minus 1 over a square. Okay, it's similar to what we did in the previous lesson. So we simplify, so we get minus 1 minus limit. Now minus minus will give you plus, right? A 0 plus a. So obviously this is 0. So as a result, the answer is minus 1. Okay. Okay, so we have finished our improper integration. So the next lesson, I will see you on week 13. So on week 13, we will go through area under the graph, volume generated by rotating the graph about the x-axis, y-axis, and also 3 different ways of solving volume rotation questions. Okay, three different ways and methods. So I hope you can try the tutorials for these few topics that we have covered online, and if you have any problem, we can discuss it when I see you on week 13. Okay, so hope you enjoy your holiday and take care. Okay, thank you for your valuable time and attention.